Swayam Prabha. Digital India. Educated India.
Welcome to the numerical ship and offshore hydrodynamics. Today is the lecture 6, and today we are going to discuss this following concepts. We discuss about the force oscillation motion, and also we discuss that how to get the added mass damping through some experiment, and also we are going to discuss something on the heave motion. Okay. So, and also this is the keyword that we are going to use to get this lecture. Okay. So, let us get back to the some board work. Now, this is where actually we finished in the last lecture, and what we are going to discuss is that at which frequency we should get that we could have the maximum response, right. In order to find that, so first we need to let us write the equation of motion and try to find out like how we can guess it. So, we write m plus a into x double dot and plus b into x dot plus c x equals to F exciting force. So, this is the fundamental equation, right. Now, what let us do one thing, let us do the the free vibration problem. So, we make this right hand side equal to 0, and also we can drop the damping term. So, let us make this goes to 0. So, then what we have? Then we have a very simple equation m plus a into x double dot plus c x equal to 0. And so, therefore, we have here just divide both the side m plus a. So, x double dot plus c divided by m plus a into x equal to 0, and this is nothing but the natural frequency, right. So, then we can define your natural frequency as omega z. So, we know that this omega z square is nothing but c divided by m plus a. So, from here we can get my omega z equal to square root of c divided by m plus a. So, that is a very common thing, right, everybody knows. Now, similar then we can find out my time period nothing but 2 pi divided by m plus a by c. Now, this is actually very important for us, right. So, now let us go ahead with this the expression, right. So, we write this omega z is nothing but the restoring coefficient c divided by mass plus added mass, right. Now, you see like now suppose you have a frequency of encounter like or that frequency of the oscillation of the forcing function is omega, and this is of course your the natural frequency omega z. So, therefore, if the both are actually morely close to each other, right. So, at that time you can expect that there is a large response, right. So, now you see before actually we started doing the hydrodynamics, we can guess so many things, right. Because if we have the idea about the restoring coefficient c, if we have some idea about the added mass A, and then actually mass of course is we know that the mass of the body. So, then we can actually approximate the natural frequency of the particular vessel, and therefore, in normal this is very important for the engineer, right. They do not that those who are working in the field, they do not have time to do some fancy mathematics or do some simulation to find out the responses all the time, right. However, for very simple estimation of the C, the added mass A, they can actually get some kind of idea about the natural frequency, and then that helps for the design, right. Okay. Now, this is something about the free vibration. So, now let us do the forced vibration problem. Now, people when you use the vibration, always they assume is a high frequency phenomena. So, people do not use it such as, so they can oscillation instead of say, right, oscillation. However, you can use anything that you like. Okay, both are same. So, now let me do some modification to do this, not modification, just rewriting the things it little bit simpler way. So, we know that this is the classical equation of motion. So, we are using like a bread and butter for you. So, you have to remember it, you can't afford to forget this. So, now you just write f a e to the power minus I omega t, this is the forcing function, right. And then let us make some kind of simplification, not simplification, I say that nomenclature, you can call m plus a is equal to a, and then let us define some term, let us say mu equal to or okay, let us take capital B equal to small b, okay, and then capital C equal to small c, and then you can define mu is equal to b divided by, let us say 2a, not mu, let us say nu. So, then okay, so that means that b by a equal to 2 nu. Okay. Let us assume this, and then let us try to apply all this thing into this equation, right. So, if you do that, then you have very simplified form, it becomes a x double dot plus b x dot plus c x is equal to f a e to the power minus I omega t. I divide the everything by a. So, I will get x double dot plus b by a into x dot plus c x is equal to f by a and divided by a into e to the power minus I omega t, right. And now, I just simply write it b by a, I just write 2 nu x dot. Now, the c actually you can see that, oh, okay, so I just forget this is c by a. Now, you know that c by a is nothing but omega z square, which is the square natural. So, we have just found out, right. So, instead of c by a, we can write it is omega z square into x is equal to f a by a, right. Okay. Oh, I forgot that e to the power minus I omega t, of course, is important. Now, again as I said that we can assume the response also harmonic. So, we can assume x equal to e to the power or with some xi a e to the power minus I omega t, and then we just going to substitute over here. So, let us see what we get. We get minus omega square into xi a, right, plus I 2 nu omega into xi a plus omega z square into xi a is equal to f a by a, right. Okay. And then just okay, if it is minus I omega t, okay, so then definitely this is minus. Okay. And so, therefore, you can find out it is omega z square minus omega square, okay, and minus I 2 nu into omega and whole multiplied by xi a is equal to f a divided by a. Right. Now, I just do little bit more modification, I just divide everything by omega z squared now. So, then what I get is 1 minus omega square by omega z square minus 2 into now nu by omega z, and you can write omega by omega z into xi a equal to f a by a. Now, remember this omega z square is equal to c by a. So, I just multiply this c by a. So, a will cancelled out, right, and then we have f a by c. Now, why I do all this exercise, because I need again another nomenclature. So, let us do omega by omega z, let us call this gamma, and then you can call that nu by omega z, you can call something called kappa, right. Now, what we are going to do is let us substitute everything back to there. Okay. Let us see what happens. Then we have 1 minus gamma square, right, that is we are getting, and then we have 2 into k into gamma. So, minus 2 I into kappa into gamma multiplied by xi a is equal to, here you can say this is equals to f a divided by my c, right. Now, you see is a very nice equation that we are getting. So, finally, we are finding out my xi a is equals to f a by c multiplied by 1 upon just 1 minus gamma square minus 2 I k into gamma. Now, how to get the so now I just do some little bit more manipulation, I just write the complex conjugate. So, I just find out f a by c, then it is 1 minus gamma square plus 2 I k gamma divided by 1 minus gamma square whole square plus 4 k square into gamma square, right, that we are going to get. So, I just break into real and imaginary part. So, it will become 1 minus gamma square divided by 1 minus gamma square plus 4 k square gamma square plus I into f a by c into 2 gamma k divided by 1 minus gamma square plus 4 k square into gamma square. Fine, clear. Now, this part is actually algebra. So, we can find out the modulus, and also you can do the tan inverse b by a, you can get the amplitude as well as the phase, right. So, let us find out what is the amplitude. So, then you can get this xi a equal to modulus of f a by c, and then if you do that, it turns out to be 1 divided by, because a square plus b square square root. Now, you have the whole square term over here, whole square term over here, you can work out, right. It turns out to be square root of 1 minus gamma square whole square plus 4 k square gamma square. So, again we can use further notation. So, again we can use this sum equal to, it is f a by c, and you can call this as some mu z, where this mu z equal to 1 divided by square root of 1 minus gamma square plus 4 k square to gamma square. Now, it has all name like you can find out there is a different name for all these things, like it is called the tuning factor, amplification factor, all these things, but we are not that interested. We just try to find out the phenomena, some phenomena, right. And of course, you can work out how to get the phase. Okay. Now, what is my interest over here, why I derive this? I just trying to plot the one thing which is the mu z, which is essentially the response divided by the tuning factor gamma, which is essentially that omega divided by omega z, right. Now, here in this location, if you put this gamma tending to 1, then you can see here it goes up to infinity. Now, if you put gamma equal to 0, right, then actually you can see that mu z equals to 1. So, mu z can be, you can say that mu z basically the response with respect to this. Now, you can see that at this equal to 1, that means when this forcing, frequency of the forcing function equals to the natural time period, it goes up, shoots up to infinity. And again very quickly it comes down and it goes to 0, because when the gamma tending to infinity, this goes to 1, right. So, gamma means this, when the omega tending to infinity, it goes to 1. So, you can see that how important it is to find out the natural frequency, right. So, we can now you can assume the no damping, of course, like if you have used some damping, it might come down, of course. So, but our idea to show all these things, just to show you that at when this natural frequency equals to the forcing, the frequency of the forcing function, there is a huge response you can expect. Even if you put some damping, definitely you can ignore this point. And also you can see that when omega tending to 0, when omega tending to 0, okay, just write this bigger so that you can get it. When omega tending to 0, you can see that response goes to 1. Now, let us see what happened that time. So, that means the mu z equals to 1. So, in that case you can see my response xi a is equal to basically the ratio between the hydrostatics and the amplitude of the exciting force. Now, you see it is very important thing, like you see that is what happening actually when you are going in the beach and you are just finding out that your response is you are moving up with the wave and moving down with the wave, and if you calculate the phase also, you can find at that particular moment when this omega tending to 0, at this particular moment this phase also goes to 0. It means that when you are in top, okay, and then this is exactly what is happening in the low frequency region, right. Okay. So, that means there is no phase first of all, and second you are moving with the wave. Now, if you see that what is happening is, see that response xi a is equals to that amplitude of the exciting force divided by the linear restoring component. What is the meaning of that? Let me write the equation again, you can understand it. See, the equation is m plus a x double dot plus b x dot plus c x is equal to f a e to the power I omega t. Now, so as omega tending to 0, what is assuming that all this, the radiation component A, the damping component B absolutely has no role in fact. So, that time the response is very simple, it is simply the ratio between the restoring coefficient, I mean the amplitude of the exciting force divided by the restoring coefficient, right. Now, this is a very important thing, because for this particular situation you really do not need to calculate all these TDRs, that all these softwares, you do not need to run all this software, and simply from the physical point of view we can simply say, okay, so this is the low frequency region, very low. So, you can assume that added mass damping that should goes to 0. So, therefore, only the dominating component is exciting force amplitude and the restoring term. Similarly, if you go to the other part of this side, when actually that the omega tending to infinity, that very high frequency region. So, that time also see the response is very small, right. And then actually from here you can see that in this equation, when omega, because if you write this, in terms of that x equal to e to the power minus I omega t, if you apply this, right, what you get is minus omega square into m plus a into xi a plus minus I b omega into xi a plus c into xi a is equal to f a into e to the power minus e to the just f a. Now, if you divide whole thing by omega square, so then what is going to happen is that your m plus a is free of omega, but then it is xi a minus now b into b I b xi a, that should be divided by omega, and then plus c is divided by omega square equal to f a by omega square. Oh, sorry, it is not 2, it is omega square, sorry. Yeah. So, then what is happening in that situation, you can see that in high frequency region your added mass become very important, not the restoration. So, you can see that in that is the beauty of this, like you can guess from this, from the low frequency region, that your restoring force become important, and in the high frequency region your added mass become very important. So, that is in vibration added mass become very important for floating structures, but intermediate region both added mass, damping, restoration all are very important, right. And actually we are going to discuss those range only, we are not discussing when omega tending to 0, we are not discussing when omega tending to infinity, we are going to discuss when omega neither in low frequency region, neither in high frequency region, intermediate region, where all this radiation component and all other component is very important. Okay. Fair enough. Now, let us now go into that how experimentally actually we can calculate the added mass damping. Okay. So, it is again a very simple thing, that suppose you have a so what is the radiation force, or is nothing but in calm water you are oscillating a body in some frequency, right, and then some pressure field generated around this body. If you integrate the pressure field, you will get the radiation force, fine. So, then but you have to oscillate here with some frequency omega, and of course, with some frequency xi a. Now, let us do that with respect to as I said, like not using the complex number, rather let us use it the cosine function. Okay. So, now let us assume that your the forcing function now now, so see you can do both, like you can assume that your forcing function f is equal to some f a into sin omega t, and then you can assume your the displacement x is f a into sin omega t, and then with some phase epsilon. but we do opposite, let us, because that is more easier for me, because the ultimate end result is same. So, we can assume the forcing function f is equal to f a into sin omega t plus epsilon or delta whatever, nothing, and then you can use that that x equal to some xi a into sin omega t. Okay. Now, what I am going to do is I am going to substitute this into the equation of motion. Okay. When I do that, let us see what I am going to get. So, now remember, like it is like your every time you need to remember this equation m plus a into x double dot plus b into x double dot plus c x equal to, now in this case it is f a sin omega t plus delta. I am going to do it for the real number, right. So, I just substitute over here. So, it is become minus omega square into m plus a into xi a cos omega t, xi a sin omega t plus b into omega into xi a into sin omega t plus c into xi a into, oh sorry, it is cos, sorry, plus C a into xi a into sin omega t is equal to f a. Now, I just break it, sin omega t cos delta plus f a cos omega t into sin delta. Now, I am just accumulating the sin term and cos term, right. So, if I do that here, I will get minus omega square m plus a, this I just try to sin omega t. So, plus c into sin omega t, and also I just the cos omega t term, which is plus b into omega into xi a into cos omega t, right. And then in the right hand side I can write this equals to f a. Now, I just the sin omega t term. So, it is cos delta multiplied by sin omega t plus, and then second term is f a sin delta into cos omega t. Now, next, as I said, it is very easy. So, just compare the sin omega t term. So, we will get minus omega square into m plus a plus c equals to f a cos delta. And if you look the sin cos term, so it is b omega xi a, of course, the multiply by xi a, b omega xi a is equal to f a sin delta. Now, you see from here you can write the expression for a, because all other term is known to you. You know the mass m, you know the xi is the harmonic, the forcing function, the displacement of the body, like you are displacing it with xi a, right. So, this is known to you, and then this force is known to you, because that is what you are going to read it from the machine. You are putting some pressure sensor to get the pressure and forces. So, this is known to you, right. And from here also you can get the damping, right. So, B equal to f a sin delta divided by omega into xi a, right. So, it is straightforward. So, to get the B. Now, from here actually this all this known to you, and then only thing is need to do that what is the delta. Now, delta also very easy. Now, if you plot it, the signal getting from your machine, this is the signal of your forcing function, and if this is the signal of your another the resultant. So, then from here you can get the information about the delta, right. So, here from these two equation you can obtain what is your added mass and what is the damping. Okay. So, today we are going to stop here. Thank you very much. So, we are going to see in the next class.